Hello, Chem 2, and welcome to the second video in this series on Chapter 3. Today we're going to focus a little bit more on the structure of the molecules and how molecular mass plays a role. So Chapter 3 is all about stoichiometry. We've already addressed what the mole is in the last chapter. Sorry. In this video, we're going to talk about mass relations. Where is that relationship between the amounts of the material in a formula as it compares to the formula? So section 3.2 is called mass relations in the chemical formula. Our goals today is to look at what percent composition is and how it relates to what's the simplest formula. The term for the simplest formula is going to be empirical formula. And then we're also going to see how the molecular formula is compared to and how that is related to the simplest formula. So let's get started. So first off, what is percent composition? Well, percent composition is the percent by mass of each element in a compound. So the way you determine the percent composition is to simply take the mass of each of the elements in a compound and divide it by the total mass of the compound. So there's a couple of different ways you can go about doing that. One of those is pretty straightforward. Suppose you have an analysis of a sample. So for instance, here I have a sample that I know, a compound that I know only contains carbon, hydrogen, and oxygen. And I know that my total sample was 50 grams. Through some analysis, and we'll talk about that in a later video, through some analysis, we find out that it's 20.46 grams of carbon and 27.25 grams of oxygen. I want to know what are the percents of all three components. Well, what we're going to do is take the mass of the carbon and divide it by the total. That'll give me my percent of the mass that is carbon. Take the mass of the oxygen, divide it by the total. That will give me the percent of the mass that is from oxygen. And then, since I know all the masses have to add up to be 100, and this compound only contains carbon, hydrogen, and oxygen, I can get the percent of the hydrogen by simply subtracting the other two numbers and then finding out the percent of the hydrogen. That's one way that you can get percent composition. Another way to get percent composition is if you have the formula. It's a little more complicated, but it still can work none the same. So suppose you do not actually have the actual substance. You're not measuring it out and analyzing it, but you do know what that substance is. Well, when we determine the molar mass of a substance, what we do to determine the molar mass of a substance is literally break down the substance into the three or however many elements there are. So in order to do this, let's see if I can get my pen to work again. Where's my pen? Nope, it didn't work. Sometimes my pen works, so there it is. So this is my numbers for sodium. This is how I figured out the amount of sulfur. And this is what I figured out the amount of oxygen. So when determining the molar mass of the substance, I take 2 times the molar mass of sodium because there are 2 sodiums, 1 times the molar mass of sulfur because there's 1 sulfur, and 4 times the molar mass of oxygen because there are 4 oxygens. And I get a total number. Now I need to determine the percent of each. And I simply do that by taking the amount of mass that I just determined in the molar mass from each of the elements and dividing it by the total. So I take my 45.9, which was the mass of sodium, when I talked about just the sodium, divided by the total, get a percent. The mass of the sulfur divided by the total to get the percent sulfur. The mass of the oxygen divided by the total to get the percent of oxygen. You'll notice that these numbers are much more precise than the numbers we got when we were measuring. That's because the numbers that are on the periodic table are derived from much more sophisticated and much more precise measuring tools than our balances we would use in the chemistry classroom. So that's percent composition. It's just the percent by weight, by mass of each of the elements in a compound. So leads to the next idea of a compound. We can think about the empirical formula. The empirical formula is the simplest whole number ratio. Example would be glucose has a molecular formula of C6H12O6. You may remember glucose from biology, C6H12O6. Well, This would be its molecular formula. Let's make my pen work again. That's the molecular formula. So if I simplify this by dividing all of my subscripts by 6, I get C1H2O1. That would be my simplest ratio. That would be my empirical formula. The empirical formula is simply the simplest whole number ratio, the simplest ratio of the compound. So how do we figure out the empirical formula of a substance? Well, here are my steps. If you have percent composition, which is a pretty common thing to have, if you have the masses, this is actually a lot easier. But if you have the percent composition, first thing we're going to do is we're going to assume we have a 100 gram total. Now, why would I do that? Well, if I had, I'll use a number, 35% carbon, and I wanted to figure out, I say, well, wait a second, what if I have a 12.2 gram sample? What's 35% of that? I got to use a calculator for that. I got to pull out the calculator, figure that out. But if I assume I have a 100 gram sample and I have a 35% carbon, that's easy. 35% of 100 is 35. Just makes that first step of the math easier. Second step would be to take those masses of each one of the elements and kind of go backwards in determining the molar mass by dividing them each by their atomic mass. Atomic mass. Now, even those molecules that are diatomic, we're still just going to divide by the number directly off the periodic table. And then the last step is figure out what that ratio is. Now, I always use, when talking about Chem 2, I always use this example because in an odd way, it kind of traps people who want to think too quickly and think that they don't have to do all the work. Empirical formula of a compound with 80% carbon and 20% hydrogen. Well, some of you might have very quickly attributed and said, wait a second, that's a 4-to-1 ratio. So my formula is going to be C4H1. Well, that's wrong. Because remember that the mass ratio is what you get when you're talking about percent composition. But what we want to know is the number atom ratio. It's going to be very different. Okay? So we're going to take our masses, 80% of carbon, 20% of hydrogen, and we're going to turn each one of those into grams. So now we have 80 grams of carbon and 20 grams of hydrogen. And then we're going to divide each one of them by their atomic mass. So we get a 80 divided by 12.0107 for 6.66 moles of carbon. And then 20 divided by 1.00, you get 19.8. And that ratio doesn't seem very convenient. It's 16.66 to 19.8. Let's simplify that. The simplest way to simplify your ratios is to do the following. Divide by the smallest. So if you divide by the smallest, and I do 6.66 divided by 6.66, I get 1. And if I do 19.8 divided by 6.66, my calculator gives me 2.97, which one of the things you have to deal with here is that you're going to have to get used to the fact that you're going to have to be close enough. 2.97 is close enough to 3 to call it a 3. So our empirical formula is going to be 3-to-1. Okay, now let's make some comments about that close enough concept idea. If I had a 1 to 1.5 ratio, I can't just round that 1.5 up to 2. I have to turn this into a 2 to 3 ratio. Those are whole numbers. So when we're on those exact fractions we know about, 0.5, 0.25, 0.75, heck, even 0.33 or 0.67, we know that this is essentially 1/4, 3/4, 1/3, 2/3, 1/2. So if we had a ratio of 1 to 2.33, I would multiply both these numbers by 3. So it becomes a 3 to 7 ratio to get whole numbers. You're going to be on the lookout for these endings. And super rare exceptions, you might have 0.2, 0.4, 0.6, 0.8. but these are the ones you're looking out for. The rest of them are going to be pretty close. So if I had a 1 to 1.49, that's going to be really close to 1.5. So then you do your multiply everything times 2. Okay. The last concept that's involved with looking at formulas is what's called a molecular formula. And if I go back to my example that I had earlier, I talked about the fact that glucose has an empirical formula of 1.121, and its molecular formula is 612.6. Well, we have to know, if we know the empirical formula, we shouldn't try to figure out, well, by what number do we need to multiply all of our subscripts by to get our molecular formula? Because with the same exact empirical formula here, we could have C1H2O1, C2H4O2, C3H6O3, dot, dot, dot. A lot of different options with that exact same simplest ratio. How much should I multiply my subscripts by? So here's how you do this. The last thing you get is a molar mass. That's going to allow you to compare the molar mass of your empirical formula to the molar mass of your molecular formula. And you're going to get to determine how much you have to multiply through by. So the steps, you're going to do just like we did before, figure out the empirical formula, nothing different. Then we have to find the molar mass of the empirical formula. Figure out the ratio of the molar mass of the molecule to the molar mass of the empirical formula. And then we're going to multiply through all the subscripts. So let's look at this example. Again, caproic acid is another compound that contains only carbon, hydrogen, and oxygen. Its percent of composition is 62.1 carbon, 10.4 hydrogen, and 27.6 oxygen. Its molar mass is 116.1 grams per mole. Question is, what's the molecular formula? Well, the first step is figure out what the empirical formula is. So let's try this one. So if first things first, I have my numbers of percentages, I'm going to divide each one of those masses by the atomic mass. So I take my grams of carbon and divide it by the molar mass of carbon, the grams of hydrogen divided by the molar mass of hydrogen, and the mass of oxygen divided by the molar mass of oxygen. And then I get this ratio, 5.17 to 10.3 to 1.73. Then I divide all three of those moles by the smallest number, and I get a 3 to 6 to 1 ratio. So the empirical formula of this compound is, again, if I get my carbs, C3H6O1. That's my empirical formula. Now, what's my molar mass of the empirical formula? Well, I'm going to go through it. I'm going to do my math. My 3 times the carbon number, 6 times the hydrogen number, 1 times the oxygen number, and I'm going to get a total mass. I find that the empirical formula has a molar mass of 58.07. Next step, divide the empirical formula's molar mass by the molecular formula's molar mass. We know the molecular formula had a 116. We know that the empirical formula has a 58. 116 divided by 58 is 2. So now we know that caproic acid, instead of being C3H6O1, we have to multiply all the subscripts by 2. So the correct molecular formula for caproic acid is C6H12O2. So in this video, we looked at how to determine the percent composition of a compound, how to determine the empirical formula of a compound, and then finally how to determine the molecular formula of a compound. All three we're focusing on a single compound. In the next video, we're going to take it across the reaction. We're going to start looking at reactions and how one compound in a substance and its quantities can be compared to another substance in a reaction and its quantities. So until next time, I will see you in synchronous time. It's during our mod 3 time frame. Sorry, mod 4. You guys are mod 4. So until then, toodles.